So I guess we can start and people will join later. So if you didn't attend any previous lectures, my name is Sabina and I'm Senior Statistician with Women Health Research Institute. So last lecture, we talked about statistical tests. So basically, it was part of what we call descriptive analysis. We want to do simple descriptive and compare groups or people in our analysis. And today, next lecture, we're going to talk actually about statistical models. So our today lecture subject is power in simplicity, unpacking linear logistic regression. So why I called it power of simplicity? Those regressions are relatively easy to understand and really easy to implement, but they're very powerful and can give us a lot of information about our data, our binary data, or our continuous variable. So objectives of today's lecture is understand the core concept of the regressions, logistic and linear, including assumption and some mathematical background for it, but I'm not going to spend a lot of time on mathematical background. I just go through slides, and if someone interested, they can review it later in their own time and check. Learn why linear regression and logistic regression are kind of the same but different because they're related to the same group of regressions. So basically, I'm going to use real life data for both linear and logistic regression. All my codes are in SAS, but codes will not be included a lot, only several. I'm going to show my way of thinking and how I perform in those regressions for actual papers and explain what needs to be done. And most important, that people and statisticians or researchers don't do, is check for assumption. Because linear regressions looks very simple. It's like one of the simplest. Everyone studied in school. But if you didn't check assumption correctly, actually your regression will give you completely different results from what you expected. So for linear regression, for logistic regression, regression is kind of a little bit more sophisticated, but actually for logistic regression, you almost don't need to check an assumption, only one, I think. So we will go. So if you remember from previous lecture, we have a detective, Rebecca called him Detective Gucci based on his outfit. So basically, last time this detective resolved a mystery about our test, what to use, t-test, for example, or parametric test, or t-test as parametric or as a non-parametric test. But now someone came to him and say, oh, I have a data set and it looks like there are a relationship, but I cannot figure out what relationship are because those are hidden. So our detective and me kind of put his glasses on, drink coffee and say, okay, this is another case when I need to decide what to do. So I'm going to look on the data and decide which regression I'm going to use and how I will going to resolve this mystery. So first type, again, we're going to talk about type of regression, linear or logistic. Linear and logistic regression actually aren't so different because they come from the what I call same crime family. Linear regressions assumes a continuous relationship between variables, and a linear regression would fit a straight line to fit the relationship between our outcome and our independent variable, or we can call it exposure variable. And it directly estimates the relationships. Yes, you have your X, Y, you estimate the line, this is your relationship. However, logistic regression, it's a bit more complicated. It's still part of the generalized linear model, GLM family. And what it means that after specific transformation on your regression, you kind of still comparing the linear regression. So you have some kind of transformation to actually review the results and get your outcomes and compare, for example, in a way of logistic regression to compare odds ratios. So it takes same idea as linear regression, but I transform it to work as probabilities. So if for linear regression, we have our X and Y, but here we transferring something into the measures of probability. So instead of straight line, we use the logit function, and logit function actually is used for binary. We can run as a type of regression with different function. It will be different type of regression. So for binary, we're going to use logit function to squeeze prediction between binary events. So basically, logistic regression uses a link function to make the relationship look like linear. So linear regression predicts a continuous outcome, for example, income, weight, temperature. The model again fits a straight line and directly estimates actual numeric values based on the input variables. So for example, we can measure relationship between age and blood pressure, and we would expect that with the age, the blood pressure is going to go up. And logistic regression will predict probabilities of event to occur. So for example, instead of giving a numeric outcome, we're going to estimate probability of binary events. Smoking increase the risk of heart disease. So heart disease, basically here we say, oh, if person had heart disease or not, and if smoking increase the risk. So basically, if the odds ratio of smoking will be higher, more than 1 to predict heart disease. If the outcome of it, as we call it, dependent variable is continuous variable, it will be linear regression. But if it's categorical as yes, no, pass, fail, survive, not survived, it will be a logistic regression. So a bit of math. So I'm going to talk about linear regression, but I'm going to use some terms from linear algebra. So if you learned linear algebra, great. If not, it's pretty simple, and I show several slides to explain how you actually can calculate coefficient from linear regression manually or in Excel, but knowing the linear algebra and formulas. So our formula is simple. It's y equal beta 0. Beta 0 is our intercept plus beta 1x and plus epsilon. Epsilon is actually our residuals. Residuals, as we talked about it before, will show us how different our actual points are from the regression line. So y will be dependent variable, x will be independent variable. Intercept in this case will predict value when x equals 0. And if you have multiple regression with all our additional variables, I reference category, and beta 1 till whatever number of variables you have, it's basically will be slope of our regression. So how are we going to do it? So this is a linear algebra approach. Yes, you basically can use linear algebra to write it down in a form of matrices and vectors and calculate your intercepts and your regression coefficients. So here on the left side, I put small example only of 3 numbers. It's age, BMI, blood pressure. And we wanted to see how age and BMI are predicting our blood pressure. So, and on the right side in the frame, this is a formula how to write linear regression in terms of linear algebra. So here, basically, the formula says that first you need to take vector x, you need to transpose x and multiply it by actual x. And after that, you need to use inverse matrix from this one, and you get your coefficient. So basically, if you want, I'm stopping on the slide. Later, you can check my calculations. And here I explain basically the formulas how to calculate inverse matrix. So basically, if you give me a linear regression to do, I can calculate. It will take a lot of time, but basically I can calculate it with calculator. And here basically additional slide of how to calculate the inverse matrix. And here basically after we did those calculations, we would receive actual regression coefficient. So we will have our blood pressure equal our intercept minus 31.43, plus coefficient for age is 114 and coefficient for BMI for 29. Of course, like having 3 records in the data, it's not actual regression, but it shows you how to do calculation. And here, actually, if you were interested in R, you can manipulate the matrices. So whatever I did manually, if you write those codes, you will get the same results I showed in previous slides. So you can look into it. So now back to business, we're going back to linear regression, assuming we're using computer and it's going to calculate everything for us. So I'm going to try to answer the question we answered for our HERBC survey. It was a lot of buzz about it in the social media and on TV. So we are submitting the first paper. So basically, our main question was how depression, its PHQ-9 total score, anxiety got 7 total score, and UTN quality of life for menopause total score affect menopause rating scale. So there's different scales, and we want to see if depression, anxiety, or menopause quality of life affecting the severity of menopause symptoms. Basically, for MRS, higher scores will talk about most severe symptoms, depression and anxiety as well, and quality of life actually different. As high as the score, as high quality of life you will have. And you can download HERBC report and look at our preliminary results. So what we're going to do for linear regression, we will check a lot of assumptions. We need to ensure that relationship between all our predictors and our outcome MRS score are linear. We need to be sure that observations are independent of each other. So basically, there is no correlation between our residuals. Basically, our error, our difference between actual values and regression values. We must to check the assumption of homozygosity. And basically, along your lines, the variance should be constant. If variance increasing or decreasing with the time, it means the assumption of homozygosity is violated. We need to check for normality of residuals, and we need to check for multicollinearity. Basically, we need to ensure that in this case, our depression, anxiety, or quality of life are not multicollinear. So how are we going to check linear regression assumptions? We're going to use I actually ran regression for our outcome for each of the scores and plotted the outcome of the regression. And it can kind of show us that both depression and anxiety score positively correlated with the outcome, and kind of residual shows that the possible linear relations, and of course the UTN will be negative relations. And here I also calculated, I believe it's Pearson coefficient. So basically I wanted to see what is correlation between all those three. So linear regression assumption independence. So we must to check the independence, and actually we can do it using specific Durbin-Watson test. And what this test is doing, it's showing if there is autocorrelation. For example, if you use an ARIMA model for time series, you will use exactly the same test to prove that there is an autocorrelation. Yes. So in this way, I put in the SAS procedure, the SAS procedure, how to calculate it. I put information in the computer, and I received the Durbin-Watson D as 1.9. And there is cutoff for the statistics. Basically, it shows if this is close to 2, there is no autocorrelation, and we have independence of variables. And if we would get something less than 1.5, we will have positive autocorrelation, and if it's more than 2.5, we will have negative correlation, autocorrelation. So everything is perfect. We proved first first assumption, it looks like it's linear, and it looks like independent. So now we're going to go to homozygosity. there is actually a test you can run. It's called, I never know how to pronounce this, Pagan test. Yeah, so basically you can Google or use ChatGPT for any program you use and figure out how to do the test. And it's done really simple. You run linear regression to obtain residuals, we square the residuals to regress them on predictor variables. If the independent variables significantly explain the variation in squared, not regular residuals, squared residuals, it means heteroscedasticity is presented. So it means we have difference on variance. It's opposite of homoscedasticity. So basically our null hypothesis will be residual variance is constant, and alternative, it's not constant, so we have issue of heteroscedasticity means we have different variance. So, and here I put how you can interpret the results based on p-values. So basically I get here, I run the test and we have number of observation, we have p-value, we have r squared. No, I think I ran regression here. We have r squared, we have adjusted r squared, we have root MSC and some other coefficient. Yes, if the p-value is significant, it means suggests that there is heteroscedasticity. Low r squared indicates predictors claim little variance in residuals, and adjusted r squared is very low. It's a confirming weak model fit. So from the plot, this is again plot from the PROC linear regression in SAS. The spread of residuals increases, predicted values increases. Yes, so it's not like straight line. It means that the residuals are not randomly scattered. Instead, they noticeably have some kind of pattern, and this pattern we can call the funnel shape. This suggests that the relationship between predictors and outcomes might not be fully linear. Yes, so basically, if we have increase in variance over the time, maybe our relationship is not so linear as we expected. Despite Pearson correlation, our Pearson correlation was relatively high, like around 0.6 for all the variables. So here we're going to check assumption of collinearity, and we all know that VIF values that they can show us if there is collinearity between our outcomes. And here I want to put your attention on something important that usually people, not everyone is doing. You can calculate VIF value with your model using intercept and without intercept. It's why it's happening. Intercept can swap some part of our possible collinearity because it's presented in the model. So what I usually do, I run the model with intercept and I do the same without intercept. And here is classical example when a intercept includes some of collinearities, spoke some of the collinearity. For example, when I did it with intercept, we could see that all our values, VIF values are less than 5. Yes, but when I did the same without variance, we could see that PHQ score VIF value suddenly becomes slightly higher than 5, and GOT7 score also closer to 5 as 456. So it means maybe our PHQ at GOT7 scores are actually somehow collinear. And if you're looking at clinically, probably like depression and anxiety might have some correlation between themselves. And here UTAN score, so basically our quality of life score in both, basically I didn't show the result, but in both cases, it's not collinear with all other scores. So linear regression assumption results. So basically, again, I run the regressions, and here I'm going to explain how you can read the results. So basically, it's giving us results for PHQ-9, got 7 in Newton score, and we can estimate it's for 1 point increase in PHQ-9 score for how much our MRS menopause severity will increase. And here we can see that for 1 increase in PHQ-9, the MRS will increase for 0.62, for GUT it's 0.30, and for UTAN, of course, it will be opposite. It will be very close to 0. And all our scales here are statistically significant. And it can be, because you can see that the for 1 point increase, change is very, very, very small, especially for UTAN score. But because we have relatively a large sample, about 1,500 people, it might be significant within like very small change. And this is like if you doing the results, showing the results or writing the paper, it's very important also not just report significant values, but think about clinical significance. If change of 0.6 is actually meaningful. Alternatively, if you want to show results in a better way, you can change for point increase. You can say, oh, per 10 points increase in PHQ-9 score, for how much my MRS score going to change. And basically, you need to create the new variable where you say, the new variable per 10-point increase will be our actual PHQ score divided by 10. So this will change your units for 10-point increase. So you can see that the model gives us several statistics. It gives us R-square, adjusted R-square, and it gives us something that's called root MAS score. So how are we going to use this MRS score? So basically, we can calculate percentage error relative to mean based on a division of our root MRS score to previous mean MRS score that was 29.99. You can look at in previous slides. So basically, it says that MRS as percentage of mean was 18.3%. So statistically, 18.3% error relatively to mean, it's acceptable, but not great. We would expect a low percentage. Also, what is adjusted R-square? Adjusted R-square is calculation of R-square when it's adjusted for all other covariates. Yes, so basically, we can see that our adjusted R-square is slightly lower than actual. So, and it suggests that like when we put all 3 variables in the model, it suggests maybe because of collinearity of our depression and anxiety score, the adjustment actually performs slightly worse than in an adjusted model. So what we can do next? Because we thinking that maybe PHQ-9 and GAT7 scores are collinear, we can add the interaction between 2 in our model and see if something changed. So basically here on the top, I put the SAS output for model including interaction, and you can see that interaction of anxiety, depression, the estimate negative and very, very small. So it's basically saying that negative interaction between those 2. So basically, if PHQ-9 and GAT7 increase together, the relationship will be not so strong as independently. So basically, we can say that their combined effect is slightly lower than the individual effects. Yes, so there is some relationships. So after that, you remember when we looked for heterozygosity, we thought maybe relationships are not linear. So we're going to say what we can do. We actually can run generalized additive modeling. So basically, they still consider linear modeling, but extend to looking for linear relationship, you're going to use some kind of spline polynomial relationship. So basically, you can add this spline to your model and see if relationship was different. So when I run this model to establish if there is like nonlinear relationships, yes, the results was similar for our actual relationship. So for 1 unit increase for depression, it's still 0.6. For gut, it's 0.3. It was 0.4 before. And slightly lower kind of relationship for U10 score. But also on the bottom, you will see the statistic for splines. So for PHQ-9 and GAT7, the spline p-value was less than 0.5. It says that there is no, it says that we confirming that there is no linear relationship. Yes, that PHQ-9 and GAT7 not necessarily linearly related to our outcome, but because our estimates from both simple model and additive model are very close, this linear relationship is very minimal. So in my opinion, if you're doing the paper, you can either present linear relationship or GAM relationship. It's kind of very similar. But here what I wanted to say, like for now, for our first paper, we presented the additive modeling without interaction results because it was like arbitrarily, you can choose any. But my personal opinion for this specific case, actually, we should run equation model, SAM. Yes, and look for each like question in any of our scales or scores or any domains, and see if there are specific questions in PHQ-9 that actually related to our MRS score and higher way. Maybe like we have 9 questions for depression, but maybe in our specific sample, only 3 questions give us very, very high score and everything else was 0. So not all PHQ-9 variables or questions is going to affect our menopause symptoms. Yeah, maybe specific. So actually our next step for this paper, because first paper was really like descriptive, we just put the simple model, but in the future, probably if it get published, I can present results for the updated analysis as well. So I would try to use structural equation model because in psychology, we often use it and see if the results were different when everything put in equations. So now we're going to the next regression. This is logistic regression. Logistic regression at this state early estimates the probability of binary event. And actually there are multiple types of logistic regression. It's why I said for binary, we're going to use logit link function, yes? Because there is binary with 2 variables like spam, not spam, died, not died. We can have multinomial regression when there is more than 2 categories. So, and here, like basically you can put them 1, 2, 3, 4, 5 arbitrary. It doesn't matter, but you also can run ordinal regression. Yes, like rating of movies or even like in any Likert scale, because it's going to rate like from 1 to 5, and it's higher rating it is, there is more higher scores they get. So there is meaning of order. And also when I talked about our parametric test, actually parametric test, Mann-Whitney U-test, it's actually a specific case of ordinal logistic regression with proportional odds methods when we actually test for stochastic superiority. And here I put definition of stochastic superiority, but if you're interested to learn what it is. So binary logistic regression. I put the equation formula. So basically, P is the probability of success, or failure. Like for example, P is probability of dying. That means probability of staying alive or survive will be 1 minus P. But we're going to take log of our probability different, and the logic function of our probabilities, P divided by 1 minus P, it actually gives us the same formula as for linear regression. Yes, and on the right side, actually, this is, I took it from Wikipedia. This is a classical representation of logistic regression. So on the bottom, you have 0 points. On the top, you have 1 point, so like failure or success. And this is how the function will link your outcome and your independent variables. So key assumptions for logistic regression, because it's kind of transformations that give us linear regression, we should have relationship between log odds of our variable and predictors. So log odds of our independent variables should be linearly related to our outcomes, and I'm going to show how to do it. Variables should be independent, and in any statistic everything will be independent. I think if someone will come up with model where something is not independent, they should get a Nobel Prize. No one ever did it. Most of regressions or models you do, there will be longitudinal or like cross-sectional simple regression for one time point. Everything will be independent. And of course, there is no multicollinearity, because if you have multicollinearity, it can bias our model. So basically, from our model, because we did log of probabilities, our coefficient will be not actual coefficient, but log odds. And those log odds can be transferred to odds ratios. So it's why I think logistic regression, it's much easier to understand, because it's really easy to explain what odds ratio. For example, for linear regression, we say, oh, for 1 point increase of something that change, we can show its graphically, but sometimes intuitively, it's very hard to look, especially if you have multi-variable regression, when you put a lot of variables, a lot of independent variables, so exposure. In logistic regression, it's really easy. If the risk of dying for specific group higher or lower than in other group. So here again, I say advantage. It's simple to interpret using odds ratios. It can handle both continuous and categorical predictors, and it's very flexible for small and larger data sets. And limitations, of course, our main assumption is linearity of log odds. It's, as any regression, linear or others, it's sensitive to outliers. And for linear regression, sensitivity for outliers can mean like homozygosity, change of variance. If you have several outliers, it will draw you variance up. And it cannot handle perfectly separated data. So what is perfectly separated data? Assuming you're doing analysis by sex, female, male, and you're checking if they're dying. So if none from female died and everyone from male died, or proportion of male died, this is a classical separated data, because we don't have events for females, so there is nothing to compare. So this is more mathematics. So this is the formula of logistic regression, and using simple math, taking the exponential of our exponential for our formula from right to left, we actually can come up with the formula that actually will explain you how to calculate our probability. And in this specific model, each coefficient better represents the change in the log odds for 1 unit increase in the predictor. So here is the example. It actually was one of the first analysis I did in the center when I started to work here. So basically in VGH, they recorded a cohort of the people that come to barn unit with some barns, and they try to build a prediction calculator, like to tell patient, if patient came with specific characteristic, they can talk to the family of the patient, like to say, oh, what are the odds of this person to survive, or how long it's going to recover. So basically, they wanted to build some kind of prediction, very simple calculator. So in this case, our outcome will be status is discharged. So basically, they went home or died. And possible predictors that they had, it's sex, age, Bow index. Bow index is something that measures severity of burns. Some comorbidities. If person, when it was in the hospital, was on ventilator, admitted to ICU, and had surgeries, like surgeries related to the injury. And we're trying to predict probability at discharge. And here our sample is very unbalanced. We had 758 people that survived and only 35 died. So basically the outcome is really good. Very small percentage of patients died, but we're still trying to explain who actually the people that died. So I ran an adjusted regression. Unadjusted regression, I included all the variables. So I said, oh, comorbidities are not relevant at all. They are not statistically significant. So for adjusted model, I only include those ones that were statistically significant. Yes, and here there is something interesting you can see. In unadjusted modeling, I think the sex was odd ratios for female to die was higher than for male, but results were not statistically significant. But when we did the reduced adjusted model, we see, oh, now sex is important risk factor because it's marginally statistically significant with p-value. It means there is something in the model that changed the model for sex to being from not significant to significant, and we need to investigate why. So being in ICU, like really increase your chances to die. If person had surgery, maybe surgery help. It's kind of protective factor. And having inhalation injury prior to hospitalization was not statistically significant. And Bow index, Bow score was very, very statistically significant. And age was not statistically significant. But in an adjusted model, it was very statistically significant. Again, say something in our model when we went to unadjusted to adjusted, something changed because a lot of components of our model tweaked around. So in order to figure out what to do, we need to run a goodness of fit test. And there's a specific test for logistic regression that we can run, post-Merrill-Lemon show goodness test. So basically, based on results of this goodness of fit, there is no evidence of lack of fit. So basically, our model is fine. Like the fit statistics are not bad. So our model is fine, but we still know that there is like a lot of things that we still need to explain. And from the model output A, it's going to give you the discrimination statistics. And it's relatively high. It's like 0.957, so it's close to 1. So basically, if you're running this classification model, you say like, oh, it's really separated those that died and survived like very well. So basically, our model in this case, our adjusted model in this case is not bad. So what we're going to go now. So on the left side, I put like descriptive analysis using what we learned from previous lecture. It's basically summary of our non-parametric test for Bow's index and age, and high-score test for everything else. So Fisher executive counts are very small. So basically, descriptive analysis helps us to understand if you have separation. Yeah, but here you say that like basically separation, you shouldn't see zero in any of the cells. Yes, when you compare in a life or die. If in one there is nothing, it may hint that we have a separation issue. So we don't have separation issue. I did the same collinearity test as before, excluded intercept, and nothing is collinear. Yeah, however, Bow's index, clinically calculated, is basically, I think, the area of your barn, calculated area of the barn adjusted to age. So age is part of our Bow index. It can be a reason why actually our age was statistically significant, but we when put everything in the same model, it's become not. So, and also inhalation injury in our adjusted model was not significant. So we might decide to remove age and inhalation injury and see if our model change and our model fit change. We can run stratified analysis, for example, by inhalation injury and sex to see if actually separating them to group change something. And there is something maybe in one group it's very different from the other. And we also need to check like what's going on between Bowes and age. So assumption checked for the logistic regression. As a visualization, you can use, and in SAS, like for example, it's built in. I can say to model, create effect plots for me. It's called effect plots. And it's graphical representations that show how predicted probability of an outcome changes across the values of one or more predictor variables in statistical model. So basically, it's some kind of graphical representation of our model. And I did it on the left side for age and on the right side Bowes. So Bowes is called TBSA plus age. So TBSA adjusted to age. So for age for both groups, and I did it for inhalation injury, yes or no. Age for both inhalation injury and not, like the probability of death is increased with age. For one group is a little bit, for inhalation injury, it's a little bit more than for non-unexpected. And Bow's index actually our perfect logistic regression classical S shape. And indicates that expected logistic regression pattern where probability of death is low and lower score and high score is we expect, because higher score will show us that the patient injury was much more severe. So basically, age is fine as expected. There is no huge difference by inhalation injury. Bow's index kind of behaves the same. So we don't see anything that say, oh, we must run it separately. So additional assumption for logistic regression now we change to ensure that our results, it's like log odds linearity assumption. So we want to see that log odds of our independent variables related to the outcome in linear way. So basically what you do, you need to create a bunch of new variables and look on those new variables to check if assumption is to check the assumption. So you create variable log of age, and after that you can create the variable when you multiply age by log of age. It's called interaction term for box Tidwell, but it doesn't matter. So basically after that, when I run my logistic regression, I put everything in the logistic regression that I included before, but I also add in those age multiplied by log age and bow multiplied by log bow to see what I'm going to get. And like for this one, age log age p-value was more than 0.5, and for bow index was the same. So there is no evidence of non-linearity. So our log odds of age and bow index are actually linearly related. So there is nothing wrong with age and bow for our model. So we now need to decide what we're going to do next. Yes, we say, oh, bow and age are somehow related, so let's add the interaction to the model, our adjusted model, and see if the interaction will show us something new. And on the right side, you have model with bow and age interaction, and our interaction not significant, so it means it doesn't matter if you put it in the model. But I also removed age and run the model. And you can see not a lot of change as well. So I think for me, for my logic is say, oh, maybe Bow score, like with the severity of burn injury, it's independent effect. Like we only need this one to decide if person is going to die or not. We can add all additional variables that we collected, but it's not going to change a lot. Our bow index still like slightly above zero. So basically, for 1 unit increase of bow score, the chance of death will be 1.09. Yeah, so it's stable. So this gives me a hint that actually it doesn't matter what I do with my model, I still going to get the same result. So technically, there's not much we can do in this case. So what additional thing I did, because we saw that the sex was not statistically significant and becomes statistically significant. So I checked how both age and TB and bow index are related to like to do the same like effect plot to see if there is anything different. And effect plot is as usual, nothing different. At all levels, age and bar severity, female consistently had higher predicted mortality compared to male. It can be because it's not like random sample. It's patients that come to ZD and VGH. And we collected data from in specific study period. So maybe by chance, female in our sample died more than male because they were sicker, there was something else, and maybe there was something else that we didn't collect our information about. So the variables that we have in the model actually not going to explain us if sex actually in this case is an important factor. But also logically, we know that probability of dying for male and life expectancy for male, it's actually lower than for female. But maybe in this specific case, females that we got, they had more chances to die. So I think there is some kind of area of uncertainty that we can do whatever we need based on the model, but we still cannot explain what is going on. But here, based on this effect plot, I can say there's no evidence of effect modification by sex. So basically, sex is not modifying our effect of, in this case, I think in our bow index to affect the death. So bow index, for high bow index, you will have more chances to die for both female and male. So what we're going to do, I said, okay, I'm going to do due diligence. I'm going to do adjusted stratified model by sex and see what I got. Because only 35 people, a small amount of female like died. So in the final model, actually only bow index and age were included and both are statistically significant. Everything else were not statistically significant in full model, and I removed them. Male, because sample size for male is much larger, basically the male results will be very similar to results for our like model for full sample. Yes, but in both female and male, you see that bow index adjusted to what we decided to adjust is still very strong predictor of death. And actually, for female, the odds ratios for 1 point increase in bow index, it's much larger than female. But bear in mind, our sample is our number of events for female are much smaller. And maybe bow index for maybe females that came to our unit during this time period, maybe their injuries were more severe. So it's kind of nature of our sample, and it's actually one of the limitation of those studies when we include everyone that came to, like patients came basically, we can assume that patient came to our clinic randomly, but it's whoever we have, and it's kind of randomness of those patients can affect the results of our models. Yeah, so basically, I think in this case, the adjusted models that included everything, including, I didn't show it, but adjusted models that included everything, it's the best model. So basically we say, oh, we had all those characteristics that we collected, we run on adjusted estimates, we put them all in the model, we get our final model. And this is a model we're going to go, we're not going to reduce anything to explain anything. For for your paper, you can write that you checked a lot of things and did sensitivity analysis and checked this and this and this. And for this specific model, and actually, after whatever you did, the only results that you can be certain that Bow index, it's very strong predictor of death in this specific case, regardless of everything else that you did. So actually, in next lecture, I'm going to use exactly the same data set to talk about survival analysis. So for this specific case, yes, we only looked in logistic regression as the band of yes or no. But bear in mind, it also depends how long the person was in the hospital. Yes, and in this specific case, maybe females stay in the hospital longer and their injuries were more severe. So basically, when we're going to transfer from logistic regression to survival analysis, as this example, we also would incorporate length of stay in the hospital as part of the model, and I'm going to explain implication, and we're going to see if changing the model for this specific data set from logistic regression to Cox regression, proportional model, and survival analysis, if it's actually did something specific. And I also going to show like what I decided to do in the end and why. So basically in the end, I'm going to use another aspect of logistic regression, receiver operating curve, to show how you can use Bow's index and how you can establish the cutoffs that say, oh, if person with a specific Bow score came to the hospital, the chances for them, or the chances of dying for them will be very, very, very high. So for summary, basically we did everything we told we're going to do. We checked assumptions for both linear and logistic regression. We looked for different tests, how to do it. We looked on outputs for all our data sets. We use real data, and I explained like my thoughts, like how I'm working with the model step by step to make my subjective probably decision what I'm going to recommend to publish. And also after the result of few models are done, because I'm not expert in specific clinical area, I send all the results with all the explanation to my clients, whoever asks me request. And I have meetings with them to discuss about like clinical relevance, what looks for them clinically relevant or not. And we finalize in like what model in the end we're going to present for abstract or paper. So basically this is continuation of our summary, and our detective Gucci really worked hard to figure out what to do. And unfortunately here for both models, I showed that whatever we decided to do in the end, and it's look like linear or logistic regression, maybe it's not, and we need to try to look for more sophisticated models to resolve the problem. But based on my experience in most of the cases, like when you get the data, most of the cases, linear regression or logistic regression will be working perfectly and supporting your hypothesis, or completely saying, oh, your hypothesis is completely wrong. Yeah. But I choose those specific two data sets to show them that it's not always so simple, and sometimes we need to go to more sophisticated modeling, at least to check if we can tease out something else to explain what's happening in our data. And probably on those models like structural equation modeling and additional like modeling, more sophisticated, are probably do several lectures next year for like a little bit more sophisticated modeling. That's it, and we have like 5 minutes for questions if anyone have any questions. And also, if you didn't understand any like something, because like I went through a lot of material really fast. If you have specific questions, you always can email me, come for me with specific question, and I'm going to prepare and try to explain to you like what's going on. Thank you.
Thank you for your presentation, Sabina. Really insightful. I believe we have one question. I'm gonna unmute.
No,
Okay. Maybe it wasn't a question. But I popped in the chat, if you haven't already signed up for session 3 and 4 on April 10th and April 24th. Everyone's more than welcome to sign up and continue learning some really great information.
And also, if you have question, you can ask question not in the chat. Like I guess it was too much information, and people kind of need to just digest. So basically, the lecture will be available like for in recording like somewhere very soon. So if you didn't understand anything or need to spend time on each slide, you can go and listen to it again and stop on the slides for more time. And if you still have questions, you can come and ask me. So here someone asked, where can we access the slides? I don't post my slides anywhere, but because lectures are recording and you can see slides in the recorded lecture, you can go through them, find what you need, re-listen to them, and let me know if anything was unclear or you have specific question on maybe how associates this, how we going to do like if you have specific question for a specific analysis that you would like to do, you can ask me like about best approach, and we can try a lot of things. And I also encourage, if you researchers and have time, I really encourage you, like maybe before you send me the data, play with it a little bit by yourself, try to do different things and come to me and we can look for it together.
Wonderful.
Could you speak to how you ended up with the adjusted models, that decisions you needed to make there? So basically, as I said, for the herbicide model, we published the generalized additive modeling without interaction just to show some results. So basically, we included same adjusted, simple adjusted table, because the paper was more like we had a lot of descriptive analysis and there are a lot of materials, but editors, when they reviewed the paper, they asked for models. So we added model, but actually for this one, I think the structural equation model will be the better choice to understand how the scales are related to each other, how each domain or each scale question related. For the second one, actually, for the final papers that I don't know that it's written and will be submitted soon, actually I presented results of Cox model briefly. And I'm going to show you next time that there will also a lot of some issues with Cox model, but I thought like I think the model is good based on like information we have. But the main point of this paper was actually ROC curve modeling to show the cutoff points. And next lecture, I actually going to show like how I did, what I did. But for logistic regression, basically, my takeaway that the bioindex that smart people developed for born injuries, it's actually a very strong predictor of your death. And if person has very high score, there's much more chances, because you can see then an adjusted model and stratified models and models with the interaction bar index was not didn't change a lot. So it shows that our index estimates were very stable. It didn't matter what we did, it still was a predictor of death. Yes, and also as any in the model, and like any review can ask you when you submit the paper, say, yes, you did it, but you didn't have those variables. Maybe those variables are related as well. But unfortunately, in clinical settings, when you're using data like from the clinical systems, like when the person coming to the hospital, there's certain information that we decided. So, for example, we don't have a lot of information of ethnicity, gender, income, other social determinants of health, so economical determinants of health. So basically, in research, we usually deal with what we have, and we need to find out the best solution possible to answer to research question we have, taking in limitation of our modeling and our data. Thank you.
Amazing. Oh, Sabina, I believe we have a follow-up question.
Makes sense. So it was so relevant to what clinical problem you were investigating and what seems relevant to include, exclude. So for the herbicide survey, we have a lot of what adjust. So survey included, I think, up to 600 questions. You can adjust for anything possible. Yes, but the purpose of the specific analysis was to show how those three specific scales affecting. So for the final model for herbicide survey, we actually adjusted. We adjusted to what we seemed relevant. I think it was access to health, like if they have a provider. It was sex, race, income, education, and access to health. And we adjusted to it because those are descriptive analysis we showed like during, we described through the paper. Yes, we did a lot of descriptive analysis. So we adjusted to what was relevant. For the second paper about mortality, those variables that decided to collect. So I only could work with variables, and I worked only with what I had. And I think based on my conversation with the residents, it's what they thought clinically is relevant. Yes, because sometimes when I receive requests, I cannot request anything I want. So basically, clinicians, when they develop their hypothesis, they also provide with variables that they are relevant. For example, I did another analysis for plastic surgery for like breast implant, 2 ways of breast implant after the cancer was removed. And clinicians come to me and say, oh, we think smoking and breast size are important factors. Maybe something else is affecting this additional variables we can adjust. But basically, they were interested in specific, like smoking. I think for previous literature review and from previous analysis, that's actually so like breast size and smoking might be the most significant effect factors. And we kind of work with it. It was very complicated. Like it's simple model, but there is like a lot of things to check. I did a lot of different modeling, and we decided what was relevant clinically based on the hypothesis what established. So it's basically, I think my job is why I like mystery stories, and I think my job is exactly as detective. Like I get the data, I start playing with it, I'm looking at it, and I make decisions step by step. But if you do any modeling yourself, it's very important to do it by the book. By the book, I mean like step by step. You get the data, you check the data, you identify all the outliers, check whatever you had, decided if you excluded any records due to missing information. So you're structuring your data set. After that, you're doing descriptive analysis and visualization, simple visualization to understand your data. After that, you go to unadjusted model and adjusted model. And of course, you check all the assumptions first. Because for linear relationship, if you have two variables and you see that relationship it's not linear, there is no point for you to run linear regression. You need to think about other alternative. In some cases, maybe based on your data, model is not necessary and descriptive analysis would be enough. So I think like most important to understand what you're doing, do it step by step, by the book. And each time when you have something, oh, sex change, let's check this, you can decide what to check for. Like if there is, what are the confounders? What is effect modifiers? And effect modifiers, it's something that masking your effect. For example, in her BC paper, we didn't get any difference for menopause symptoms by race. And we would expect maybe, but actually in our specific sample, visual minority participants had high income and high education. So in this case, maybe income education, it's effect modifier for the race. So maybe like if basically we can say if our participants, white and not white, had the same income and same education, maybe we would see the difference between two groups. But because our specific, because of the nature of the sample, and in this specific case, visual minorities had high income and high education, the effect of race was masked. So you can do it as stratified analysis. You can do like a lot of things to tease out to actually figure out what additional characteristic might affect your outcome. Yeah, I think we over time.
Fantastic.
Yeah.
Thank you, Sabina, for sharing today.
Thanks. So next time we continue with this data and we see what we're going to get. Thank you and have a great weekend ahead.